To continue our review, I wanted to talk about Kirchoff's laws next. So hopefully you've seen these before, and hopefully this is review. So there are two of Kirchoff's laws. The first one we'll talk about is Kirchoff's voltage law, sometimes abbreviated KVL, because it gets used so much we don't want to have to say the whole name. And this is also called the loop law for reasons you will remember shortly if you don't already. Okay, so Kirchoff's voltage law states that the sum of the delta V's, the sum of the changes in voltages for each component around a closed path meaning it, goes back to where it started. That is, it is a loop around the circuit equals 0. And this is true no matter what loop you pick, as long as you end up back where you started. This is a result of the fact that the voltage only has a single value at every point. You can't have a single point in the circuit that is at 1 volt and 5 volts. It has to only have a single value. So what that means is if you traverse some loop and add up all these delta V's, you have to end up back where you started. If you end up at some different value of V, then there are two values at that point, and that's nonsensical. So anyway, the point is Kirchoff's voltage law is not mysterious. It really just kind of comes out of the math of these changes in voltage as we move around. So a very simple example without doing any numbers. Imagine that we have a voltage source over here and several resistors in series connected with that. So we'll say this has voltage VB. We'll say this is resistor 1, resistor 2, and resistor 3. So we are to imagine traversing the circuit in a loop, and there's only really one loop here because everything's in series. Maybe we start in the lower left and we go up to here in the upper right, and then continue going around the circuit clockwise, and we end up back where we started. So for each hop of this journey around the circuit, we have delta V's to add up. So the sum of our delta V's looks like the following. So when we go from here to here on our battery, we are going from the negative side to the positive side, right? This is the short line, this is the long line, so this is the positive side of the battery. So if we're going from here to here, we must be increasing our voltage. So our first term is a plus VB battery voltage. Then continuing on resistor 1, at this point we will have to guess what direction the current is flowing in order to figure out whether the voltage is getting higher or lower. It's okay to get this wrong. If we get this wrong, the worst that happens is we end up with a minus sign in our final answer, and it's not a big deal. We'll see many examples of that before too long. But with a circuit this simple, we can guess correctly that the current is going to go clockwise around this, right, from high through the resistors to low potential. And so that means if our current is flowing clockwise, that means this side must be at a higher potential than this side of resistor 1. This side must be at a higher potential than that side of resistor 2. And this side must be at a higher potential than this side for resistor 3. So the consequence of that is that when we have our next delta V step across resistor 1 from here to here, we are decreasing our voltage by an amount equal to the voltage on resistor 1. So we have minus V1, where V1 is the delta V drop across resistor 1, and the same for V2 and V3. And we'll see if I can fit these on the line. All right. Okay. And Kirchoff's law tells us that when we do this, this equals 0, and that, if we knew actual values for the resistances and some voltages, we could actually solve this for a useful quantity. Right now, we can only really do one thing with it, and that is rearrange this. So this is our equation, right? VB minus V1 minus V2 minus V3 equals 0. We can move V1, V2, and V3 to the other side and get VB equals V1 plus V2 plus V3, which is not a trivial result. This is actually important to know. The battery voltage here, whatever voltage the battery is, 12 volts, 20 volts, whatever you've connected to your circuit, that has to equal this voltage drop plus this voltage drop plus this voltage drop. That battery voltage you're applying is getting split up between those resistors in such a way that they still add to the same value. Or you could say this voltage is getting divided between those, and we'll talk more about voltage dividers next class probably. All right, that's all I have to say about the voltage law. Let's now talk about the current law. And now you will see the advantage of the abbreviation, because I don't even have to write Kirchoff's current law. You already know what I'm talking about. This is also known as the junction law. And the current law is as follows. So for any node, which is another way of saying a important point on the circuit, and so in our circuit, often this current law is most useful when this node or point is a junction between multiple wires, two or more wires. So we're going to, keep this general for any, really what it's saying is for any point on the circuit, this has to be true, but it's most useful where there's a point where stuff is coming together. You'll see. All right. So for any point, the sum of our currents into that point has to equal the sum of our currents out of that point. This, so like how the voltage law came from just kind of this mathematical argument, the current law comes from conservation of charge. So the idea here is that if we have a point on the circuit, we have some amount of charge flowing into that point, and we have some amount of charge flowing out of that point. If those currents are not the same, if we don't have the same amount going in as we did going out, we would be building up charge at that point and like accumulating like a literal pile of electrons. That can't happen. Electrons repel each other. They want to spread out through the circuit, and they will, do their best to avoid piling up because of that. So, so this is just a result of conservation of charge. All right, let's do a little quick graphical example the way we did before. So maybe here is part of our circuit where there is a junction between several wires. And let's say we have a current flowing to the right, I1, and maybe we know these currents, or maybe we already know the directions of these currents, maybe we don't. If we don't, we have to make guesses for them as we do with the voltage law, and sometimes they're right, sometimes they're wrong. Sometimes you get a minus sign, not a big deal. So, in a situation where we have currents that are going in directions like this, the sum of the currents in, so plugging into our equation, the sum of the currents in, well, we only have one current going into this point, that is I1, and that is equal to the sum of the currents going out of that point, which is I2 and I3, right? Both of these currents we have said are moving out of this point. And there you have it. The amount of current going into this point is equal to the sum of the current going out, or in other words, the colloquial way of saying this would be the current 1 goes into this point and then splits into current 2 and current 3, so that those currents, you still have the same total amount of current if you add those together. Some people don't like splitting because there's this hint of it being 50-50. Of course, that's not true. How this current splits into two depends on everything that's connected to that. So it could be, 10% of the current is here and 90% of the current is here, or, any combination you can think of. So that is all I have to say for Kirchoff's current law. We'll have some examples with numbers to come very soon, but hopefully this is a good refresher. Before finishing today, I wanted to say one other thing, and that is that Kirchoff's laws do not just apply to circuits with resistors and batteries. So at least in Physics 211, when I teach it, most of the circuits we end up analyzing are, batteries and a few resistors, and that's it. I don't want that to give you the impression that these equations only work for circuits like that. In fact, Kirchoff's voltage law and current law, because they come out of these very fundamental things like conservation of charge, they are true for any circuit, and so they will continue to be useful throughout this class. We will use these in some form or another on basically every problem. So it's important to me and to you that you get comfortable with both of these and kind of be able to use them and see where they would apply without having to think too much about it.